Hello, my name is Brandon, and welcome to the next video in my series on basic statistics. If you're new to the channel, it is great to have you. Welcome. If you're a returning viewer, it is great to have you back. If you like the video, please subscribe, give it a thumbs up, and share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. So now that we are introduced, let's go ahead and get started. So in this video, we are going to learn how to find the mean of grouped frequencies. Now, unfortunately, this is often a topic that is skipped in stats classes, and that is very, very unfortunate, because learning how to do this is quick, it's easy, and it's extremely helpful when you're looking at other people's studies specifically. And if I may say so as kind of a data nerd, it also shows you some interesting qualities underlying statistics. So let's go ahead and get to work. So here is the underlying issue and why this technique can be extremely helpful. So sometimes you may not have all of the original data. You may only have a frequency count table for certain groups or bins of data. So for example, you might be looking at a study or reading someone else's work or something else in a magazine, whatever it might be. And all you have available is something like, well, there were 14 people in the $25,000 to $34,999 salary range. There were 19 people in the $35,000 to $44,999 range, etc. That's all the information you have. Or you may only have a histogram that shows the number of observations for each bin or group. So you may not even have a table. You may just have a histogram, and then from there you create a frequency table. Now the issue is that you want or need to calculate the mean for the entire data set, but you don't have each individual observation to use to do that. So while finding the exact mean using this method can be done, there is a way to obtain a very close approximation to the sample mean. Now I will say that using this technique, the higher the count or the frequency in each bin or group, and the narrower the bin range, the better the approximation will be. So here is the frequency table we're going to use. So we can see that we have in the first row a lower salary of our bin or range of $20,000 and then an upper salary in that bin or range of $29,999. And in that range, we have 30 observations. $30,000 to $39,999, we have 20 observations in that range, etc. Now, just for the sake of this video, I am going to make one small change to this table, and I'm going to do this. What you will notice is that I've changed the upper salary to be just rounded up to the next sort of $1,000. Now, I know what you're saying probably, hey, Brandon, this is not right. This is not the proper way to do that, because which bin does $30,000 or $40,000 go in? Does it go in the one above it or the one below it? I understand that. This is strictly for demonstration purposes only, because it makes the rest of the video a bit easier to understand. And honestly, it doesn't really affect the math that we're going to do here in a second. It's strictly for the sake of this video. But what it does mean is that, just so we are clear, a salary of $30,000 will go in the second row. A salary of exactly $40,000 would go in the third row. So we're just changing that upper salary range to make the math a little bit easier to do here in a second. So you might only have a histogram with frequencies. So if you're looking through a magazine or a news article or a study or something like that, you may only have this. So using this histogram, you could actually make your frequency table like we saw in the previous slide. So again, we'd have 30 people in the first range, 20 people in the second range, etc., etc. So if you only have this histogram, you can still do this type of problem. So this is called the midpoint method. So since we do not know each individual data value, what can we do to get an approximation? So the best resolution, and I mean resolution in the sense of like precision or like the focus of a camera or something like that, the best resolution we can aim for is the midpoint of each bin or group interval. And the midpoint is very easy to find. It's simply the upper bound plus the lower bound divided by 2. Of course, it could also be the lower bound plus the upper bound, because addition, the order doesn't matter, divided by 2. But you get what I'm saying. So doing this simple math, we'll find the midpoint of that bin. So for example, if our bin range is $30,000 to $40,000, again, this is why I rounded up a couple slides ago. It's simply 40,000 plus 30,000 divided by 2, and that is $35,000 for our midpoint for that bin. So here are the midpoints for all of our rows. So you can see that our first midpoint is $25,000 because that's halfway between 20,000 and 30,000. The midpoint is $35,000 for the second row. You see how this works. Now, one thing I do want to point out in this table is the frequency column. You can see this frequency column is sort of a weighting process. So what we're saying is that there are 30 observations in this first row, but there are only 20 in the second row. So in our original data that we really can't see because we don't have it, what we're saying is there are more observations in the first row than in the second, and therefore we have to weight that accordingly. So step 1, we multiply each midpoint that we found by its frequency, which was the last column we saw. And again, this is a weighting process. Step 2, then we sum all the values from step 1. Step 3, we then divide the sum from step 2 by the overall number of observations in our frequency table or that we've counted up in our histogram. So for example, for the first row, we would have a midpoint of $25,000. The frequency is 30. Therefore, we have 25,000 times 30, which gives us 750,000. So the MF there is the midpoint times the frequency. So here's the calculations for every row in our table. So we have 750,000 in the first row, and then we have 700,000 in the second row, 630,000 in the third, so on and so forth. Now remember the idea of weighting I said before. If you notice that even though the salary is higher, the midpoint salary is higher, say in the third row, it's $45,000, there were only 14 observations that were in that range. But if you go up to the top row, even though the midpoint salary is $25,000, the midpoint times the frequency there is 750,000. So it's a combination of the midpoint and the frequency, which gives us our sort of weighting process for the overall sum. Now we go ahead and do our math, and we end up, when we do the division, of $68,300. So using just the frequency table or the histogram, what we've done is using the midpoint and the frequency to calculate that in this mystery data set that we don't have access to, that the average or the mean salary of everyone in this table, all 200 observations, is $68,300. So here are the results. So the mean salary using the grouped frequency, like I said, is $68,300. We did not have any of the original observations to calculate that. Well, I kind of lied. I do have the original data. And what I want to tell you is that the mean of the original data, all 200 exact observations, is 68,403. Look how close it is. So using this grouped frequency method, we calculated $68,300. The actual mean is $68,403. So in terms of accuracy, we're about 99.85% accurate. And again, this calculation down here is just a rough estimate of accuracy, so don't at me or anything. But what we're saying is that we are basically within $100 of the true mean using just the frequencies from our frequency table or histogram. So one question is, why does this method work? And this goes back to what I said at the beginning about some really cool underlying facts about statistics that I find very interesting. And actually, if you really understand them, it will help you understand more advanced statistics as you go. So think of each bin, that range, as its own little sample of the overall data. So that little sample contains only the values in that bin. So if I recall correctly, remember the first bin from $20,000 to $30,000, we had 30 observations or 30 individuals. Think of that as its own little sample. What we know is that if we were to take the mean of just the data in that bin, of just those 30 observations, again, we don't have the original data. Well, we do, but we didn't have the original data. If we took the mean of that, the result would be close to the mean or the middle of that bin. And this is very important. It's a very important thing to understand in statistics. So if we had 30 observations or access to those 30 observations in that bin, if we found the mean of those 30 values in that first bin, guess what? That mean would, we're pretty sure, be close to the midpoint or the center of that bin. And that's why we can use the midpoint as an approximation. So as I said, that mean would be pretty close to the midpoint of the bin. So we are estimating that within each bin, on average, the values would converge around that midpoint. So if we had access to all 30 observations in that first bin, we found the mean of those observations would be pretty darn close to the midpoint that we found earlier. Now the frequency we talked about kind of weights the midpoint for each bin. So we're saying that this bin has more observations than this bin, and therefore when we do our sum, we are weighting them accordingly. So therefore we can use the midpoint as sort of a stand-in for the observations, sort of a stand-in for the mean of those observations in that bin that we don't know. That's pretty cool, isn't it? Okay, well, I kind of lied again, sorry. So here's the proof. So I went back to the original data and broke everything into the 10 bins that we looked at, and I actually found the mean of each bin. So in this first bin, the actual average, or the mean of the salary data was $25,676 and some change dollars. We had a midpoint of $25,000. So that's a difference of about $677. So the absolute value of that difference is about 2.64%. Now, if we go down to the next one, the mean of the second bin between $30,000 and $40,000, the actual mean of that bin was $35,205. The midpoint was $35,000, and therefore the difference is only $205, which is 0.58% of the absolute value of that difference, and so on and so forth. So as you go down, you can see that in the third bin, 0.69%, $314 difference. Then we have in the fourth row, a $57 difference between the actual mean and the midpoint, which is 0.10%. So if we go down all these percentages, you can see just how close the actual mean of that bin and the midpoint of that bin are to each other. Now I made this final column the absolute value so we don't have negative or plus signs messing us up, but realize that any difference that's negative would have a negative sign in front of it, and any positive one would be positive. So if you were to average out all the positive differences and the negative differences between the actual mean of each bin and the midpoint, that's where we got our accuracy before of 99.85%, which I think is pretty amazing. So that is our video on the mean of grouped frequencies. And again, this is something that a lot of stats classes skip over for some reason. I'm not sure why. It's a very useful technique on several fronts. You can find means for data that you don't even have at your disposal, so long as you have the histogram or the frequency table for that data. And again, it also reveals some underlying characteristics of statistics that are very fundamental, that are very foundational to understand how statistics works going forward. So I hope you enjoyed the video. Thank you very much for watching. I appreciate your time, and I will see you in the next video.